So we have about 1 hour, 1 hour 20 minutes. So I will try pass through lecture 4 and where we start, okay, where we finish about this modeling. So we have model, scene, input are scene, wind turbines, sensor, and output is radio frequency signal. It is our reflected signal that contains all reflection from wind turbine, one or multiple. But honestly, our simulator works with multiple, even wind turbines, even consider multi-part effects, but it is extremely numerically demanding. And I think that it's much better use it for designing of, like analysis of one wind turbines, because results for multiplication for multiple of wind turbines, it start be so big messy that even you can't much recognize from these results. So I will generally focus on one wind turbines. So scene, I already mentioned that is everything in the environment except the wind turbine and the radar itself. It could be vary from simple model to complex 3D model of environment. We just make free space plus ground reflection, and the ground reflection is very easily just changing of amplitudes. And wind turbine, it is complex model because it must be described it very precisely. It is object of interest with all parameters, tower, blades, and so on and so on and so on, how you see later. And sensor, of course, it must be really careful modulated also. PRI, PRF, kind of different transmitted pulse. And then every this input, of course, I forgot in PRs also carrier frequency and so on and so on. And all this input go to model, and output is signal, reflected signal from wind turbine. And these signals in the form of IQ data, so it is like it is complex signals, IQ data. So we know information about amplitude and phase. Of course, we need both when we count in with speed, so we need also phase. So first input is scene, wind turbines, radar, then we put everything to model and we get radar echo, reflected signals. It is reflected signal, so it is in time domain. What you can see on oscilloscope, it is time domain signal. But of course, what we are using for visualization, we take these signals and compute Fourier transform and spectrogram. So spectrum and spectrogram. But we still storing a complex signals value, because you never know what do you need for another analysis. Maybe you want to use wavelet transform, something else. So we are storing signals, but all what I will present you will be based on spectra and spectrogram, of course, because there is best visualization for us. So, oh, you see well, I didn't see well. Okay, there is several category of approaching how modeling. This is not related to wind turbines. It is like general approach. So we have macroscopic view and analytical model. It is non-FEM. It is classic, and it uses simple geometric optics, radar cross-section formula, specular reflection from tower blades, and it is exactly what we are using. Physical fidelity is from low to medium, so it is, of course, don't include reflection from environment, atmospheric reflection, and so on and so on. But for discovering this phenomena, how you will see later, is not so important. It is for, so then is system level behavioral models. It is simplified representation embedded in radar simulators. It is physical fidelity is medium. Then is full electromagnetic full wave models. They are good, they are much better results, but you can take one blade and compute radar cross section in some distance. But imagine if you are doing on carrier frequency 10 gigahertz, lambda is 3 centimeters. How many reflectors you get in blade that has 160 meters? How you won't compute this one? It will be so demanding. And you will compute static reflection of one blade. And you need to do it for any movement of 3 blades. Forget. It will be better results, but I don't think that is possible to modulate. Plus, imagine that you want to modulate also reflection from environment. It is just out of my imagination how will be complex. So, next is hybrid multiscale models. It is combined macroscopic blade tower geometry with localized EM solvers. This is not bad because we just think about the update of our algorithm. Now RCS, we discovering that like we are using RCS that is unit. So it is mean every part of blade element has same RCS. It is big simplification, but we could replace this by real RCS, something like this, because what will be? It will be some metrics of values only in specific environment. So we want to do it like this one, but we want to do it like this one, but it is like future. I will talk about lecture 8. So it is general modeling approaches for radar reflection from wind turbine. And now how we continue. What is our base model parameters? It is number of wind turbines, position of the wind turbines relative to primary radar system in Cartesian coordinates, number of blades, height of tower, wind turbine blades length, range of rotor blade rotation frequencies, so how quickly, and a nacelle rotation relative to position of radar. Because there is so many angles, if you understand me. You have radar, rotation, antenna. You have, how to say, you have wind turbine with respect to radar, different angle. You have blades that is rotating in different angle, and you need always compute all reflection to your blades, to your element. So there is it is very complex geometry. It is clear message. Everybody understand what we are doing, but it is so many angles, how you will see later, that is really hard to evaluate, but we have it well. So, and if you will, and how we will compute, we divided tower, we divided each blade, we divided to elements, small elements. Size of elements is variable, so we can make smaller, bigger, and this influence number of computation, of course. So if we will do it smaller, it will be high density computation, higher it will be low density of computation. And we just think that signal from radars go to each element and we compute reflection. And what will we do it after compute all reflection from all elements, and in each time instance, because it is rotation, it is movement, then we will make summation of all, at what we get? One signal. One signal that is changing in time, and it contains all information. So it is very, very complex task. Also, when we make tutorial 4, you will see that when you run it, even pre-process simulator and data on my laptop take it a relatively long time because, and it is pre-process. I can't work with raw data. So this is base geometry. This geometry you will see very often, these lectures and other lectures, and I will start with static parameters. Coordinate system, so position of radar, position of wind turbine in Cartesian x, y, z. So clear, I think. Then static is turbine description, individual parts. So for us, tower, rotor, and blades also, but they are movement. But never mind, you can just use it for static. What is mean that is movement? That for another time will be in little another position, but you can count it that is always static in every position. So it is individual part. Then nacelle yaw angle with respect to PRS. And what is this? It is not this angle, this angle, this. It is this. It is this angle, if you get my point. It is this one. And imagine this is still rotating, so this angle is changing. It is like angles in 3D. So clear? Then for us, like generally, how works this? What is for us very important parameters? Distance. It is slant distance, like in radar, classic. And this distance is not same. Because look, it is this distance, this distance, this, and so on, and so on, and so on. But you can compute only one. Why? Because it is static and it is not moving, it is not rotated, it is tower. So there is first optimization which we made. You will pre-compute only one because it is still same. Then we have this distance to nacelle, and this is like small circle that is rotating but never or not rotating, but it is not important. It is like 1 point. I know that in reality it's not 1 point, but for a reason it is not important, so it is 1 point. So this distance is also static parameter. Do you agree? This is one size, and this is this distance. And now imagine that this 3 blades is rotating with some number RPM. Sorry, it is in Czech. I don't forget to translate this one. It is rotation speed, some frequency of rotation speed, and each blade is divided to blade length, blade element. And now imagine it is rotation in time, and for each time instance, like this is 1 time, you need compute distance to this to each element. Then you will make movement about some time instance and compute completely again and again and again and again and again and again. You get my point. It is a huge number of computation. Also, this looks like blade. It is picture, but we not consider that is blade. We consider that is tube, only tube. I know it is big simplification because the blade shape is very important, but you will see that result is not big difference from reality, and we need to do it. This simplification if we want compute by this way, of course. But in future, if we will replace this blade by metrics of real RCS, if we will get this data, then we just multiply it with another number. What is RCS? It is just number. So it will be some matrix computation. It not will be something different. So this is important angle. It is this yaw position, and this angle, it is like position of rotor with respect to radar cross section. If to radar, if you get my point. So be careful. There is multiple angles. It is not so easy, and it is statics parameter. Then we have kinematics parameter, and it is rotational speed of the rotor. Initial blade phase, it is this angle, because we need start. And you can tell me, okay, and what you are choosing. What do you want? How you will see later. It is not so important. It will influence your results, but I will show you how you can make easily correction with your measurements, so it is possible to correct, because it is random variable. It is depends when you start measuring, and I don't know where will be this position of blades. Then is rotational speed of antenna, and it is the worst case. Imagine you computing all these distances, but not only distances. Distances only, it is parameter about distance, but what we need to compute? All Doppler shifts, all speeds of blades, for all time instants. And imagine that even this one could be rotation in the movement. So it is, geometry is relatively easy. We just computing reflections. But imagine that is all moving, even this one. So it is not mean that in one time instance I will recompute. This antenna is slightly rotating, and now it could happen that I don't see 3 blades. I will see only 2 blades, or only 1 blade, on 1.5 blades, or. And what is the worst? When make rotation, all angles will change it. So task is easy and understandable, but you need to compute. So geometry is clear. Each blade is divided to individual blade elements. Blade element represent elementary reflectivity. So we say that will be 1 or something. It is not important. It is just number. And exactly, but it is important is that we can replace this number by real RCS, because it is already there, this matrix of reflexibility. But only we just for simplification use some unit value. I don't say 1, but you understand me, some unit value, constant value. Okay, if we will have better results, it is mean some better approximation of real RCS, we just replace values by another values. But model is not affected, it is still same model. So it is good one. It is simplification of uniform RCS of these elements, because we need to do it. And it is tube, it is not definitely shape of the blade, because it is not possible to recompute. Because imagine that I even can't imagine how I will do it in MATLAB, because if I will modeling this one, it could be only through RCS. So if I will get this RCS, okay, why not? But I have a doubt that I can sometimes get it. Okay, I can get it for some specific angles, but not for all of them. For all rotation, for all combination. And of course, imagine if I will just change a rotational speed of antenna or rotational speed of wind turbines, it is another values. So it will be relatively very complex. So calculation of position of blade elements, and now I will talk about position of blade elements with respect to radar, is based on PRF, because imagine we just talking about, and it is another funny thing that I told you about sending calculation of distance, but we are in radar. We are not transmitting the whole time, but only small part of pulse. So I need also count how long this pulse needs to get to this blade element and reflect it back, and to each element of each 3 blades, to each tower, and everything is variable in time. If will be continuous way, okay, I watching and just gathering data reflection signal, and it is relatively not easy, but easier than our case. But we work in pulse regime, so I am sending pulse and getting answer. So it is much worst case, this one. So and another thing is that rotation speed of wind turbine is completely different from rotation speed of radar. So sometimes you see, sometimes radar antenna can detect, see wind turbines, sometimes not. So it is another thing. After computation, this slant range from individual blades element with respect to PRS, we use it computational reflected signal of all VT. Then we make summation of all signals, and result is reflected signal. But this, I call it slant range, but of course it is complex. It includes also this moving rotation, so it is this shifting in frequency, it is Doppler effect. So it is base principle of our simulator that we develop, or model. I never know if I use it simulator or model, because it is just covering both. So there is a list of parameters. First one is type of transmission signals. You can use just rectangular pulse without inner modulation, with inner modulation, and so on. Honestly, we use mainly without any modulation, because it is enough. It is not so big influence to affect it of our radar signal, and it is more simplified. But it is one function. If you want another, just simply choose another function. Type of modulation or signal compression type, again, you can use what you want. Pulse repetition frequency, it is FPRF. Carrier frequency, it is clear, it is influence our Doppler. And wavelength, of course. And in input parameters in number and dimension of VT is position, X, Y, Z, because there is, it is looks like it is in plane, but it is X, Y, Z, it is in, you can choose it. Height, blade length, blade rotation frequency of wind turbines, initial rotation angle of wind turbines blades, number of elements on a single blade, and rotation of the wind turbine's nacelle axis relative to PRS. It is wind direction, because of course your wind turbines always try check it to best one, so it is clear at 90 degrees, because it will be best reflectivity. So, Kenya? There is geometry. All this was related to one turbine, and now I will show you case that will be multiple wind turbine. But when I will use multiple wind turbines, we are back in radar. You know that radar has all area divided to range cell and Doppler cell. It is great. So multiple wind turbines scenario is only if multiple wind turbine is in one resolution cell. If it will be like two wind turbines and each in individual cell, you can compute independently, completely. So it is mean if will be really close each other, then you need to compute multipath reflection, and so there is some influence. But if will be like, if we will have grid and each cell will be one, I can behavior like it is 1, 1, 1, 1, 1, 1. If you understand me, because there is not important. So it is related only if will be in one resolution cell. And then we discover that there is this combination. Imagine this is one resolution cell. And what's happened? Okay, I have one signal that check. I don't know. Okay, I will start there. This is direct signal and back signal. Direct back, it is clear. But then these signals, blue one, travel through this, this, this. And then can this, and can travel this, and all this combination. So what is number of combination? 1, 2, 1, 3, 2, 1, 2, 3, 3, 1, 3, 2. So you can see color coding of combination. So it is example of combination of two considered reflection. So only I consider two reflection. We discover that dependency between 2, 3, 4, 5 reflection, because of course there can be multiple reflection then go to radar. Forget, it is too complex, and with each reflection is signal more attenuated. So we just discovered that maximum is 3 reflection, but better 2 reflection. But again, only in one resolution cell. If it will be separate in each resolution cell, forget. You can behave with this simulator like there in each resolution cell is only one turbine. Why? Because you are interested only each resolution cell is independent. So I will compute responses of signal in this cell, this cell, this cells. But I don't need consider multipath because it is independent each cell. So only in case that you have more wind turbines in one cell, then you can use it multipath. And resolution in the results will be very low in the results, because honestly the attenuation is so big that I think that you can neglect it and always work with wind turbines, even like wind one. Of course, imagine if your radar will be at 100 kilometers far away from wind farm, and wind farm, then radar cell could be like 3 multiplied by 5 kilometers. Okay, then in one range cell you will have really big amount of wind turbines. But on other case, you will be 80 kilometers far away. How many cell will be affected on this one? 3.5 kilometer like example. Why? Because of course due to like radar cells with higher distance, it is bigger one and bigger one and bigger one, but it is still one cell. So you get my point. If it will be closer, it will be affect me more, but it will be separate in each cell. And if I will be far, okay, it will be multipath, but it affect me only one cell. Okay, ignore it. So it is like you need to think what you exactly need. So now we go to influence of wind turbines on radar spectrum spectrogram. Due to high range of tip peripheral speeds of individual blade elements, there could be speed from 0 to, of course, when it's shut down, to 220, 240 meters per second. It is about 800, 900. It is just speed of classic plane that I arrive. It is classic, it is about this speed. So, receive Doppler spectrum components caused by blade elements reflection occur within the entire equivalent range of blade element speed. And we will go to this one. Imagine that you have 5 rotation per second or something like this, or per minute. It is not important. What will be speed of this one? Relatively low. This one higher, this one higher, this one higher, and so on. This one very high. So it is increasing. So it is mean Doppler shift of this will be low. This will be higher, 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 higher to some maximal, because there is maximum speed. Is it clear? And what will be result? Results will be that in spectrum or spectrogram in time will be all Doppler shifts, because you will make summation, because it is one reflection surface, but each element rotation with a different speed, plus pulse transmission, plus rotation of radar, and all you need to compute well, and results will be one signal. So the spectrum components highly variation in time, highly vary in time, because there is almost all components caused by this Doppler shift, because there is almost all frequencies due to this fact. Of course, it is clear that some has higher amplitude, lower amplitude, and it is variable, and on which depends on it. Also on, how to say, this radar, this depends how is. If it will be like this, and this is radar, the distance to each element, even through rotation, will be constant, because it is circle, so it will be constant. So how will looks spectrum? 0, just tower. And if it will be like this, the speed will be maximum, because you understand me. And if it will move like this or like this, so it will be maximum, and you will see the biggest Doppler shift. And everything between, it will be something. So, each element move with different instantaneous radio velocity, I already told you, and Doppler spectrum of the turbine is spread over the wide range of frequencies. It is important message. And of course, I already told you what will be biggest influence. End of the blade tips. This one, of course. The biggest piece, biggest Doppler, biggest amplitude. And it will be for case that is like this one. And also change distance, because if I am there, distance is like this. If I am there, distance is only this. So this is 0 Doppler shift, this is maximum Doppler shift, and everything between is everything between. So we discovered that there is 2 main phenomena in the spectrum domain. First is dominant spectral component end of the blade tips, and it is our primary focus for mitigation, because you can't predict the whole spectrum of each element. It is not possible. So we, from this all range of elements and all range of Doppler frequencies caused by this movement, we just make simplification. Okay, what we will do it if we will just mitigate this 3 biggest one, and not only exactly these 3 values. I mean some small range around these values, it will help us, because this small around nutshell, it is small rotation speed, this not cause it so big problem. It is almost static, if you understand me. Some small plus minus 2-5 Hertz of Doppler shift, okay, MTI filter, we will handle it, it is not so important. So, dominant spectral component is clear now. What is it? It is the end of the blade tips because due to high speed. Then we have flash. Flash is strong short duration events when blades are aligned specularly with the radar. What is mean? Radar sending electromagnetic wave. It is wave. It is wave. And imagine sometimes happen that blade position and this electromagnetic wave will do it this one. Like each element will be reflected with maximum intensity, if you get my point. It will be exactly right position that will be like maximum. And this we call it flash. And what do you think? How will look this spectrum in case that just flash occur?
It will look like something is detected target.
It is all looks like target. So no. It will looks like the whole part of your spectra from zero frequency to maximum Doppler frequency will be maximum. It will be like constant maximum. So it is mean you don't have chance to do it anything with this. Why? If I will mitigate this flash, I will mitigate everything what is inside because it is maximum. So, but I have good news. This flash occur only about 5% of time during operation. But during this time, forget. You don't see, but it is for like approximately 1 up to 2 milliseconds. Good. It's not so bad. But how you can recognize something when is whole spectrum saturated to maximum? You can't recognize anything. It is so saturated because each position, due to each position, you get maximum reflection, and all this reflection just go back to radar. So, and this phenomena is flash. We ignore this flash. Even if we model it, we could model it, we try it. It is not for mitigation. I can say during this flash, ignore, because I can't recognize. It is not exist any type of target that will beat this flash, if you understand me. It is so high. So it is not necessary to model and work with this because you just need to ignore these flashes. But during rest of 90% you can mitigate this DSC component, but it is only 3 of them. So we make simplification from 1,000 and million of them to 3 of them. And this is possible to modulate. The biggest contribution on this has my friend and colleague Dr. Karel Jurica, that he worked on this during his PhD studies, and he like majority with me developed this model. So I just want to mention that is of course not only my work, it is this discover of DSC component is his work. And there is example that now we will talk about dominant spectral component, and this is example of spectra. First rotation, second rotation, third rotation, 4, 5. Imagine that you have radar and start rotating, and always I see wind turbines only through some short period of time. So it is spectrum of first time, second time, during second rotation, third rotation, fourth. And check this one. Do you see any prediction of this? It is look like random. And where is this DSC component? It is first blade, second blade, third blade. First, second, oh, I lost it blade, where is it? Probably covered by tower. First, second, third, first, second, third, first, second, third. You can see they are still moving and moving due to this blade speed and with different position and so on and so on and so on. So is it clear, this description? Normally you should see always 3 maximas plus on 0 Doppler you will see stable maximum. What is it? Tower, reflection of tower, 0 Doppler. I don't care, MTI filter is enough, it is static. So I can easily remove this one. It is same like this one. But check rest. Do you see any periodicity? No. In spectrum. This is example of this. These 3 points, it is 3 these points. With if I will move in spectrogram like example this, it will be like second turn. If I will move to 5, it will be 5. It will be this one. Do you get my point? So, this red line didn't exist. It is just visualization for better visualization. But do you see in spectrum looks like random movement. 1 sine wave, second, third. It is 3 harmonic signal. Why? 3 blades. What is angle difference? 120 degree. It is classic example that you can relatively easily simplify problem of almost from infinity reflectors. Okay, so if I will mitigate these 3 sinusoidal frequencies, then rest is relatively low. And what this mean? If there will be target, I will see amplitude. So there is no issue. So I need to mitigate this 3 plus tower, but tower is not problem. So it is our mainly Karel Jurica contribution in with founding that this is quasi-periodic movement, but we can found it in spectrum, but later when we found it spectrogram, you can see, yes. No. Imagine that this is 1 maximum, second, third maximum. If you will make cut like this, maximum 1 will be there, second and sorry. If you get my point, if you will make cut, then values is always very cross section of this red line. So it is like you have 3 harmonics waves and always make a cut. So it is this 3 maximum amplitudes because there is spectrum, but spectrum in time. So each cut is 1 spectrum from 0 up to 20 rotations. So it is first spectrum, second, and so on. And one thing, it is relatively hard to understand what is this cross. Okay, this is spectrum, but what this mean? You told me that this is amplitude, right? But what I have on this axis, Doppler, it is amplitude, but units are hertz. If you get my point, because it is this values. It is like this is amplitudes, of course. There is specific Doppler frequencies, and I need to mitigate this one. You will see later when we do it, this mitigation technique with UKF filtration. So these three hills in each spectra is strongest DSC component that we want to mitigate, and we call it dominant spectral component. And if you will mitigate this one, then will be some rest of this between the maximas. And what is this between maximas? It is reflection of different blades element, but their contribution is lower. Why? Because they have lower speed. It is not, and they have so not bit reflection. Only this, they at the end of speed is the end is reflection. So instead, we won't try to modulate the whole spectrum. We ignore it. We won't modulate movement of these three maximum components, DSC component, and if we will do it and we know how it works, then we could make mitigation technique how remove it. So is it clear? This is the same I want to show you. It is like Doppler spectrum at time 0, and you get tower, one blade, second blade, third blade. So you can see, and this reflection where will be position depends on mutual angles, how I already explained. So this you can see this individual points, and there if I will mitigate this place, this place, this place, this place, this is relatively in a similar level like others, like noise, spectrum of noise. So it is mean that my target not will be masked. I need to remove only this part, these three parts from spectra. It is also not so easy task, but still it is not so complex. So can I continue? So DSC component is so random. It is periodic or quasi-periodic and tightly linked to mechanical rotor speed, of course. Because if rotor speed will be higher, what's happened? This maximal side of Doppler will be higher, and they will travel through higher distance, like this contribution movement. Why? Because it is higher speed, higher Doppler, so it is clear. And the tip blades, each wind turbine blades rotates with some angular velocity omega r in radian per second, of course. Angle per second, it is changes its angular velocity or radial velocity. I don't know which version you use it. So this radial velocity could be described like angular velocity multiplied by r. What is r? Blade of length, multiplied by cosine function omega rt plus phi 0. So what is this one? Initialization angle. And so it is like free blade system, 120 shifted. So first blade, second blade, third blade, ABC, they have like this behavior. Doppler spectrum produced will be FDT 2 VR divided lambda, so it is this one. You can see, and we are in Doppler spectra. And this we want to try modulate. But now looks that is not so complicated, if you get my point. So each blade tip generates one sinusoidal Doppler shift. The total reflected signals becomes a sum of the three sinusoids phase shifted by 120 degrees. And what is the best one? It is almost identical to the three-phase sinusoidal system in power engineering. It is the same. And it is probably very well known for you. So there I just put physical interpretation of analogy. Of course it is not same, but everybody knows this three-phase sinusoidal system. Everybody use it. And influence of wind turbines for radar is the same. So we have rotating three-phase magnetic field, induced voltage 120 degree. We have rotating three-blade rotor, produce three-phase shifted Doppler modulation. Same. Similar principle, same principle, not same, of course. Electrical output is sinusoidal voltage. Radar echo modulation is sinusoidal Doppler shift. Okay. Harmonics appear if magnetic distribution is not uniform. Harmonic Doppler components appear due to geometry and blade asymmetry. Same. This three-phase voltage are sinusoid shifted by 120 in time. Three blades is separated by 220 in azimuth, and the three tip signals are again phase shifted by 120. So it is free voltage analogy. And everybody knows this analogy, so it is easy to understand. We always need to figure out how to explain people easily. And okay, it is free nice analogy, but it is true. It is true. So, and what is good, it is relatively periodical. Of course, I maybe better use quasi-periodical. It is periodical, but there is some little differences due to different RCS because we don't model it exactly well. But it works. So, can we use this periodicity of DSC for mitigation? Yes, because it is periodic. And if it's periodic something or quasi-periodic, because what's happened if I will slowly start changing speed of rotation of blades? What do you think that happen? The sinusoidal frequency or period will be shortened or longer. So okay, there will be some breathing, how I say it, but it will be extremely slow in comparison of transmitted pulses because it is just milliseconds. But I discovered that starting time of wind turbines from 0 to some nominal rotation speed in modern cases is about 10-15 minutes. And with sending milliseconds, microseconds, it is for us is almost constant. And if it's something almost constant in period, okay, I can predict where will be in the next time and next time and next time. And if I can something estimate or predict, I can design filter and mitigate. So, and why we focus on this? There you see picture without this red line only, because this is like example to understand well. Result is this one. So you can see that this is biggest values, of course. And why I want mitigate this biggest one? Because there will be masking of target. But why not there? Because there not will be so big masking, and I can relatively ignore in the rest. And what is mean this area? It is this area or this area. You understand in this area? Oh, of course, there will be some influence. I don't tell that not will be. Yeah, it is, but much lower. And it is possible that very weak target will be masked, still will be masked. But some bigger one or middle one, it not will be masked, and I will show them. So my task is relatively done. Okay, I design something what relatively works. And few words about flashes. Do you see this? There is still sine wave. Do you saw it? 3 different sine wave. And one time, like typical time duration of flash is 1-2 milliseconds. And during this period, all is in the phase reflections, and you see just full spectrum. How will looks there? It will be like constant. Full spectrum. You can't do it anything with this. Okay, I can ignore or mitigate, but I will mitigate everything because I can't recognize what is useful information, what is not useful. But just stop thinking about this because it is, you can't do it anything. So during these times, it is true, mitigation algorithms failed. I don't know how other companies, maybe they have some solution, but I have doubt about it, because how you can recognize something what is 1000 stronger reflection than your target? I don't think that is possible even. But if you lose connection with your target for 1 millisecond, 2 milliseconds, never mind, because you have tracking algorithm, so it is mean they predict movement of target, and target can't move like in one way and after 1 millisecond to another way. It's not possible because it is plane. It is not any huge, even helicopter can't do it this quick movement. So it is clear that I never mind during this flash, I still have my tracking algorithms that during this short period where I don't know anything, they will cover because they predict where will be. It is just prediction, it is true, but never mind. Okay. The observed turbine spectrum, this spectrum what I already show you, it is not influenced only by wind turbines, but by a lot of radar parameters. And we are again back, and for this reason I need make lecture 2 for you about this radar, because consequence of limited sampling frequency causes Doppler effect, aliasing of Doppler effect, and it is done by PRF or PRI, inverse value of PRI. And again we are back. If I have PRF with some setting, and my maximal range of Doppler will be 1 kilohertz, and Doppler speed caused by wind turbines tip blades will be 2 kilohertz, I have problem, because there occur aliasing. And what's caused this aliasing? That this with higher rotation frequency, this so-called amplitudes, sine waves will be higher, 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 and when I reach maximum, then not continue like this one, but this copy will be aliased to this one, because it is aliasing. Copy of spectra. You know probably what is aliasing. You are working in spectral domain. Little? No? But you understand me. It is like mirroring. You are outside of range. You have range, some range. And if you are outside, this will be copied to this. To same, like if you have minus 1100, it will be 900 in this case. Always it is wrapped to same region. It is sampling theorem, but you know sampling theorem. It is same. Sampling theorem. If you, I don't know, as example, my voice have maximum frequency 20 kilohertz or bandwidth 20 kilohertz. How you need to sample? Double time, 40 kilohertz. And if I will undersample, aliasing occurs. So all this higher frequency will be mapped to my base frequency. And it is the same, it is completely the same. This amplitude will grow to maximum and then should continue, but due to my limitation, this will be mirroring to the same in same time, but it will be happen there. And this aliasing is little problem. Why? Because when occur aliasing, it is no more sinusoidal wave, because it is due to aliasing and due to reflection. And in this case, the mitigation method, of course, will have little problem. But honestly, this not happen very often. Why? Because rotational speed of your antenna, it not will be always maximum Doppler shift. It is happen some time by time only, due to worse scenario, how I can say. So it is not so big problem. And again, if you design good filter, like Kalman filter, nonlinear Kalman filter, then Kalman filter is relatively robust to handle it for some time, of course, only for some time. If then this will still continue, this error, you will have big problem, because Kalman filter failed and can't predict this values well, and what's happened, okay, DSC component are back. But we make analysis and it was relatively enough stable. Okay, it is about this Doppler speed. I already show you. No, I didn't show you. It is dependency about aliasing. Imagine it is influence of the carrier frequency on the chain in Doppler frequency at different radial values. If I have, like example, 10 gigahertz, then in 10 gigahertz speed of target 1 meter per second cost me Doppler shift about 70 hertz. 5 meter per second about 220, and so on. So you will make cut and you will see. But imagine if I will have if I will have only 100 megahertz. So what will be? How will be Doppler shift on 26? It will be 10 megahertz. What will be Doppler shift of this one? Oh, we are out of range. We can't recognize it even. Why? Because we have too low carrier frequency. So of course, and it is this aliasing, how is converted back. So higher frequency give us very good sensitivity on low velocities, but they suffer from Doppler ambiguities. And again, we are back. We do it during the whole morning, during tutorial and yesterday. So lower carrier frequency, higher unambiguities, it is better, but low sensitivity to low target velocities. It is against. Okay, you have low unambiguities, but for low speed will be bad. If for low speed will be good, you have ambiguities. And again, you need to find some balance between this one. So you can see that this is really dependent on radar parameters. And it is about aliasing. I already told you. I think that I must skip. So I just this end. PRF must be high enough to cover the expected blade tip Doppler frequencies without aliasing, but still low enough that we maintain a reasonably unambiguous range in distance. But it is terrible requirement because goes each other. On one side high, on other side low. So it is hard to balance. And you need to understand that sometimes you can't even change PRF in radar. You can usually, but only in some small range, because it is designed for this type. Okay, I think I know that still will have some free time, but I would like stop now because there will be the wall block that is related together, and I would like to finish tomorrow if never mind. But yesterday time delay, I think that we relatively catch because I speed up number 3, so I have only 20 slides missing today, so it is not much, so we will continue morning. And do you think that you won't start at 9 or 10? It is up to you.
He's the coordinator of this.
And it's not possible.
So regarding the schedule of shift also, he said that he has sent the schedule to IIT Hyderabad, but we will manage in that shift. But 9, I think maybe it because it's getting online link also.
Yeah, okay.
So 10, exact 10 will be okay, sir.
Okay, so exact 10, we will stay on this, no problem. We just make reduction of this 2 hours gap, it is okay.
We told that is possible, that lunch we are shifting 1 hour and the last 1 hour we are managing.
Okay. So we start at 10 like usually and we'll continue, but it will be not 2 hours lunch but only 1 hour lunch, and it will be better and we can go about 1 hour earlier and I fulfill my duties. Perfect. Thank you very much for your attention and we'll see each other tomorrow. Thank you.